program, anyway, in the program you see I planned 2 lectures. One lecture is about sound radiation from structures, and the other lecture is about inverse acoustics. I have reduced the lecture on sound radiation from structures to the minimum I would like to tell you, also because it is connected to inverse acoustics. And the one about inverse acoustics, I have also compressed it a little bit. So altogether, I want to do this in 45 minutes, but I'm not going to rush. So don't worry about that either. And another good news about this talk is there is very little math in it, and the math that is there is like very clumsily written, so nothing difficult. So before we go to those things, I would like you to listen and watch these 2 videos very carefully. It works? Oh no. Oh, this is bad. I really need you to do this, so I will go to a different place. Let's see. It's a different lecture, but it doesn't matter. This one should work. That's one, film number 1. Presentations, you can think about the question, and the question is, what do these 2 movies, these 2 sounds have in common? That's the question. Start thinking, you can start talking also, you can shout something at random. Anything, I mean, there's more than one answer, there's more than one right answer.
Resonator or a vibrating body?
A vibrating body, yes. More.
They're both awful.
Not the first one, come on, shoot. Really? I didn't know a double bass could do that. I really love it, this music.
Yeah?
Yeah. No, that doesn't count. Any other similarities?
Low frequency.
Low frequency. Okay, I will tell you the answer. They have everything in common, really everything in common. So what do they have in common? This. They are caused by exactly the same physical mechanisms. And I will show you that. So of course, we are not going to look at everything today. That I hope you understand that. But the physical mechanism is the same. So let's see if I can convince you of that. Let's start at the source. So in both cases, the source is a vibration source. So in the case of the double bass, the strings are the vibration source. And in the case of the car, what we heard in the movie, it was mainly engine noise. But one has exactly the same kind of situation with tire noise. So let's take the tire. Let's say the tire is the source of vibration. Then in both cases, we have a transmission. In the case of the double bass, it is the bridge that transmits the vibration of the string to the soundboard. And in the case of the car, it is the suspension that transmits the vibration of the tire to the car body. same thing. Then once we get at the car body, or in the case of the double bus of the soundboard, we get the sound radiation. So for the double bus, it's obvious, the soundboard is the sound radiator. For the case of the car, it's maybe less obvious, but everything in the car, the roof, the windshield, the doors, the floor, radiate sound. So when we hear a structure-borne sound in the car, it is not the tire we hear, it is the car, which is a huge soundboard. So I hope you are convinced now. These two problems are exactly the same. The only difference between them is our purpose when we design it. Because when we design a double bus, our goal is to make it sound as nice as possible. While when we design a car, our goal is, on the one hand, to have a low noise level, and nowadays more and more to create a certain sound environment in the car. So the goals are different, but the physics of the two problems are the same. But today, we are only going to look into the soundboard. The reason I showed you this is because I love this music and I wanted to share it with you, but also because this is what I do. So most of my work is about this chain and understanding different parts of these chains for different applications. So in order to understand sound radiation from plates, because this is what I'm going to talk about, one needs to understand waves in structures. And as you know, in structures we have several types of waves. We have longitudinal waves, we have shear waves, we have bending waves, and all those waves behave in a different way. But I am today, well, and of course, sorry, this bending wave is the important one for sound radiation. So for sound transmission, one needs to consider all types of waves, the axial waves, the shear waves, but for sound radiation, the responsible waves are the bending waves. So this slide, I'm showing you this to notice one particular thing. And it is that, so we, starting from the basics, which is a string and bending waves in a string, we see that the wave equation, because it is a wave equation, in the case of the string, looks very much alike with the wave equation for sound waves in air. And the wave speed is a constant wave speed, so it has a certain value which depends on the tension in the string and on the density. But the main point here is that for a string, when it's bending, the wave speed is constant. That's the main point. This is what you need to remember. Because if we go to the beam, next step, and let's make it complicated, but a little bit complicated, the equation looks like this. Again, the solution of this equation is, let's see if I can use this properly. Yes, it's a wave. If we put the solution there, we find this relationship between wave number and frequency, and this has to scare us a little bit when we see this. Because as you see here, we have k to the power of 4 on the one side and omega to the power of 2 on the other side. So this doesn't look good. And if we continue, and to find this wave speed for bending waves, we see this square root of omega there. So what we find is that for bending waves in beams, the speed depends on frequency. So it's not constant anymore. So that is the essential difference between a string, constant velocity, a beam, not constant, frequency dependent. And the same holds with slightly more complicated equations, but in the end it's the same thing. We find for the plate, again, the same expression. Please note that the wave speed of the longitudinal wave in this case is slightly different because we get the Poisson ratio for the plate. We didn't have it for the beam. But essentially, it's the same expression. Okay, and now, what's this? How is this called? This is what we call dispersion. So when a wave has this property that the speed of the wave depends on frequency, then we call it dispersion. And it sounds very scary, at least that's what I thought the first time I heard it. What does this mean, that the wave speed depends on frequency? But in fact, it is very simple. It simply says that if you are a very big, tall guy, like Rick, very big, very tall, very long wavelength, then it will take you quite a while to get here. But if you are small like me, short wavelength, then you will be the first to get here. That's dispersion, very simple. So big, slow, small, fast. That's all. And well, I found this, it is a very simple animation, but it gives you the picture, I hope. It's some MATLAB stuff, but so all these frequencies start together, and you see, if we wait long enough, as I said, the small guys are there before the large guys. That's all. So remember that when you see this wave speed expression. So, and why, because that's of course the next question, why is dispersion important for sound radiation? Why? Well, this is the reason, and I will explain what we see here. I'm not going to talk about this group velocity thing, so we are talking about the phase velocity, which is the ratio of omega to a wave number. And what we see here is frequency on the x-axis and wave number on the y-axis. And this is what we call a dispersion plot. And in this dispersion plot, we see this line that corresponds to waves with a constant wave speed. Those waves are the acoustic waves. So they have a constant wave speed, so the relationship between frequency and wave number is a line. For bending waves, it's dependent on frequency, and it will have a shape like this. And the crucial issue here is that at a certain value of the frequency, and the wave number, of course, these two lines will cross. Well, not cross, they will intersect. And at this point, this point we call it coincidence. And what we have there is that the acoustic wavelength is equal to the structural wavelength. So the wavelength of the bending wave in the structure is equal to the wavelength of the acoustic wave in air. And this frequency is a coincidence frequency. One can, as you see here, calculate it simply by saying that the two wave speeds have to be the same. And it is important for radiation because strange things happen when one gets to this coincidence frequency. And we are going to look into that now. So, yes, this angle theta, it took me quite a while to understand it. So, don't try too hard. So what we have here is an infinite plate. And we have this bending wave in the infinite plate. And lambda b is the wavelength of the bending wave, and lambda is the wavelength of the acoustic wave. And what you see here, these lines, is what we call the wave front. So this angle theta is the angle of the wave front with the plate. So we can show that the sinus of theta then is the wave number of the bending waves divided by the wave number of the acoustic waves, or in other words, the wavelength of the acoustic waves divided by the wavelength of the bending waves. And you see already this sinus theta is going to give us problems is if the wavelength of the acoustic wave is larger than the wavelength of the bending waves, because then there is no solution for this. There is no theta because this ratio is larger than 1. So the question is, what happens then? I skipped a lot of equations. I wanted to show you this. This is the expression of the pressure field radiated by the infinite plate. And I need you to watch two things. One is this, square root of 1 minus kV divided by k squared in the denominator. And this exponential factor here. Those two are important. And of course, we see that when these two are the same, the pressure goes to infinity, which is of course not true. That's impossible. But remember, this is an infinite plate. An infinite plate doesn't exist. But in theory, the pressure would go to infinity at coincidence. But the question is, what happens when we get to the situation that kV, the wave number in the structure, is much larger, or larger, it doesn't need to be much larger, it's simply larger, than the wave number in the acoustic field? What happens to this exponential factor here? Because right now, if k is larger than kV, this is simply a harmonic function, a sinus or cosinus. But if it is the other way around, what happens to the exponential factor? So it's an exponential decay, yes, or increase. Okay, yes. You know, I got this question from the students. Why do I choose the negative solution?
Depends on your definition of the square root.
Yes, but the solution of the square root is, of course, plus minus whatever.
The definition of the square root.
Of your definition of the square root.
You define your square root in a certain way, and then you have to choose one, plus or minus.
Yes, but you have to choose.
Yeah, you have to define it. Yeah.
Yes,
yeah.
yes. Anyway, you choose in a way that when you go away from the plate, the waves decay. That is the choice you make for the sign. So this exponential becomes a decaying exponential for positive y.
Sure.
And what does this mean? And these are nice animations Rick made very long ago. But they still work, I still use them. So what you see here is, at the top, you have the situation when the acoustic wavelength is smaller than the bending wavelength. So let's say we have these very large waves in the plate and very small waves in the air. Then we have, I don't know how to start it here. I will do it like this. Then we get this. So what we call propagating waves. So as you see, the bending wave in the plate is traveling in the plate, and then these propagating waves are excited by the bending vibrations of the plate. These are propagating waves, and this is what one gets. One is at the situation where the acoustic wavelength is smaller than the bending wavelength. But if the acoustic wavelength is larger than the bending wavelength, then we get this exponential decay, which looks like this. So what happens is that the air which is excited here goes back there. So you get what they call hydrodynamic short-circuiting. But basically, you see that the velocity oscillation travels with the bending wave, but it doesn't really go into the air, to say it like that. And for this, Miko always uses an analogy to explain how this works with the long wavelengths and short wavelengths, and I heard him do this in a course. So imagine you are sitting in bath. It's Miko's analogy. So you are sitting in bath, and you want to make waves in the water. If you use your hand and you move it slowly, you won't be able to make any waves. The water will escape and go to the back of your hand if you move it slowly. So that means you have small structural wavelength and very large acoustic wavelength. Then you cannot radiate if your structure of your hand is small compared to the wavelength you want to radiate. So what can you do? You can go fast. So the wavelength in the medium you want to radiate is also short, so you get in a better ratio. That's one option. You go fast, then you can make waves, you can test. The other possibility is you take your arm and you move it slowly. Then you will also make waves. You have to try it. Try it and you will see, you will understand.
There is another analogy, and that is when you have a bullet that moves in the air, then when the bullet is subsonic, then nothing happens. But when the bullet is going supersonic, you get a shock wave. Yeah, a Mach line shock wave. And your wave crests at the surface are moving subsonically in the lower and supersonically in the upper. So the lines you see in the supersonic are just shock waves of a supersonically moving bullet.
That sounds much more fancy than this bath thing. I have to remember that one.
These wave crests, in this case, move supersonically. So they create shocks. And this is moving subsonically, like when you move with your bicycle in the air, you don't create shock waves. I just go around.
Thanks, you. Now we have two explanations to choose of.
Water is a difficult problem because water has no dispersion.
It's nice to think about sitting in bath and playing. Anyway, so this brings me to the next thing that is used to explain how plates radiate, and is this concept of radiation ratio, which, if you think about it, it is rather artificial, I would say, because someone thought, I don't know why, possibly Shure knows why, of comparing the radiation of the structure itself to some reference radiator. And this reference radiator is the piston. And what's a piston? It's a rigid surface which is doing this with the same average velocity as the original structure. And we take this sound power as the reference, and we compare the sound power of our structure with the piston. And that's all. And this is what we call radiation efficiency. So, well, what you see here then is how to calculate the sound power of the piston. But let's get to the expression, which is the interesting thing. So in the end, this radiation efficiency for the infinite plate is simply this. So you see it's some function that tends to 1 with when the structural wave number is much smaller than the acoustic wave number. So when we are in the supersonic situation, and for the infinite plate, it doesn't exist when we are in the subsonic situation. And at coincidence, here you see the graph. So this part is the supersonic part. There, the radiation efficiency is infinity, of course, at coincidence, and then it goes to 1. And below coincidence, it doesn't exist. In the Sound and Vibration book of MWL, it says that when you include damping, also for infinite plates, you find some sound radiation below coincidence. But it's the only place where I have seen it that they say this. Normally, it is always explained like this, that below coincidence, no radiation for the infinite plate. But plates are not infinite. You see that we have here room full of tables. A table is a plate. And it is interesting because plates, you know, we can explain the vibration of plates as a combination of modes. We can always say it's a summation of the response of vibration modes. So what we know is that when these modes are vibrating at frequencies which are subsonic, so below the coincidence frequency, then they are bad radiators. And it depending on whether they are odd modes or even modes, they can be bad or very, very bad. And what does this mean? Well, I tried to show it with these pictures. So what happens, let's go back. So we have this mode, let's take the odd one. And if the structural wavelength is small compared to the acoustic wavelength, then what we get is some hydrodynamic short circuiting between this part of the plate and the neighboring parts of the plate. So we get dipole cancellation, we call it. So this plus and this plus cancel out with this minus, let's say it like that, and we keep radiation only at the edges. And this is what one calls edge radiation. So this kind of radiation pattern, let's say, can only be found when you are below coincidence, so when these modes are bad radiators. For the even modes, it gets slightly more complicated, but it's the same principle. So we have quadrupole cancellation, so plus, minus, and they cancel out. And here we have dipole cancellation, and in the end, we only keep the corners. So that's why they are called corner radiators. And you can imagine if we go very, very, very low in frequency, at the end, these two will cancel out each other also. So, but if you do a measurement with the acoustic camera, you can see these kind of patterns in the radiation of plates. So it really works like this. And what happens when we are in the supersonic situation, that's the easy one? Well, it's very simple, because one can simply say every half wave in the plate, to call it like that, is a monopole. And you will see that. If you make these sound images, you will see a mode like this, when it is above coincidence, radiating as single, separated monopoles. And how does this translate into the radiation efficiency of the plate? Well, at high frequencies, we have roughly the same behavior as for infinite plates. So at high frequencies, we have this kind of behavior of the plate. And at low frequencies, where we have this kind of behavior, where we get very complicated curves, and there is no analytic solution for the sound radiation of plates. So this kind of curves are quasi-empirically determined curves, which can be built by pieces, let's say, but basically you see the radiation efficiency is much lower than 1, and it becomes smaller and smaller as the frequency decreases. So this is the finite plate, and well, these are the conclusions, and this is the presentation for the sound radiation from structures. If we put the presentation on the website, I will put all the slides there, so not only what I showed here. Okay, is this a good idea? Because there is more background information for that. Yes. So now I suggest I continue with the next, yes?
Can I I've heard about something called cymatic frequencies. Can you?
Cymatic frequencies.
Cymatic, yeah, with CY. I don't know, maybe you don't have time for that, but if in YouTube you type cymatic frequencies,
yes,
CYMATIC, then there is a group that have made some kind of a video that there is also this vibration of plates at different frequencies, and that's one part of the picture.
Suggestion.
I've seen that.
I do this evening, and we can have a look at it tomorrow. Then I can think about it, see.
Yeah, just
Okay. Okay? Cymatic. Yeah, I'll do that.
One small question.
Yes.
Finite plates, is that free in the air, or are they just in an infinite larger plate? Is there a coupling between front and back?
For the expression I show here, for this one, you mean how this one is determined? That one is, I believe, for the baffled plate, simply supported baffled plate. Would that be? I'm not sure.
So there's no connection between front and back.
No.
Then you would always have a monopole, so the efficiency would not go down.
It will go down. Also in the case of the baffled plate.
Also.
Yes. Good. So if there are any urgent questions, I will go to the next presentation. And how am I doing with the time? Okay, I need to cut it down a little bit. I see more than I thought. So I think I will skip some bits. This one is shorter, so it should be fine. But so. This presentation is about inverse acoustics, and inverse acoustics is very closely related to sound radiation from structures, because in fact it is about using the sound radiation, measuring it to identify the sources. So the problem in acoustic imaging is a very obvious one, I would say. So when we have a source, we have a bunch of microphones. When we look into the problem of sound radiation, as we just discussed, that is what we call the direct problem. And inverse acoustics is, of course, about the inverse problem. So we measure something, and then we want to know what this source is. That's inverse acoustics. And, well, I will skip this one about the information. So we will focus here on near field acoustic holography. And near field means, as you see, that the microphones are close to the source. And why do we put the microphones close to the source? Because we want to capture both propagating and evanescent waves. And if we do that, in theory, one could have unlimited resolution. So normally in the far field, one is limited by the acoustic wavelength. The resolution is limited by the acoustic wavelength. In the near field, in theory, could be unlimited. And the reason is this, but I think Rick will talk about this more possibly, yeah? So I will continue. This I think you will also show, so I will continue also. This is basically about showing why the near field is important, but believe me, it's important. You will hear why later. So we continue with the methods. And when you read about near field acoustic holography, you will realize that there are many methods, and some of them I summarized here because they are fundamentally different in the way they approach the problem. So we have the inverse boundary element method. I will tell you about that a little bit. The equivalent source method, I will also tell you about that. Fourier-based near field acoustic holography, Rick will tell you about that. And then we have the methods based on the elementary wave model. I'm not going to talk about that. In those methods, what people do is use a set of predefined base functions. So for example, in SONA, they use a set of plane waves to describe the field, and then try to fit the coefficients. But in this one, in these Helmholtz equations, these squares, they use spherical waves, for example. So if you read about it, the main thing here is that they use a set of base functions. But what I'm going to do now is first talk about the common features of these methods. Because in the end of the day, all these methods work more or less in the same way. So we are going to look into that first. So what is the general idea? As I said, we have a source, take an engine for example. We have a source-free region, and we have the hologram we measure, which is you need to realize here that each pixel is 1 microphone measurement. So, and then given this information, we want to find the source. That's the situation. So the first thing we need is some relationship between the pressure at the source, and the pressure at the hologram. And this relationship, you could call it a transfer matrix. And I put here omega in between brackets to stress the fact that we get 1 image per frequency. So this process of reconstruction, we do it for every frequency of interest. That's why I put omega here. And P, you have to see it as a vector with the pressure at all the measurement positions for the hologram, source with the pressure at all the reconstruction positions, and H is the transfer function matrix between those. So in general, we can, very often you will see also, you see it here, a relationship with the velocity, because very often we are interested in the vibration velocity at the source. And then you will find a relationship between the velocity at the source and the pressure at the measurement plane, and this is again a transfer function matrix. So typically, the source could look like this. This is 2 loudspeakers we measured at the lab. And if we want to solve the inverse problem, well, one could say, assuming that the 2 vectors have the same number of elements, we just invert those matrices and we are done. You could think that it's a square matrices, so why not? Well, if we do that, if you do it, you can try, then you will get this. And why will you get this? Because this problem is ill-posed. So due to noise in the measurements and also in numerical experiments, even the small noise one has numerical experiments, leads to this kind of rubbish if one simply inverts the matrix. So what one needs to do to find this, which is what we want to find, is regularize. So regularization, the problem of deciding how much you have to throw away, let's say, how much do we want to throw away, how much do we want to keep, that's common to all near-field acousticography methods. And the most common one, just for your information, is Tikhonov regularization, where you basically have, on the one hand, the difference between what you measured and what it should be if you multiply the source information with the transfer matrix, the norm of that, and then you have the norm of the solution, we call it, so of the velocity at the source multiplied by a weighting function. And then one can show that for this problem, this is the solution. So this inverse matrix is what we call the regularized inverse, and you will see it most often in this form, which is called the standard Tikhonov regularization. So when this L matrix is the identity matrix, then they call it a standard Tikhonov regularization. And of course, the key here is to find the alpha that will give you the best reconstruction. So in practice, it will look more or less like this. This is a way of representing it that is used often. On the x-axis, we have the error of the reconstruction, so the difference between source times transfer and the measured hologram data. And on the y-axis, we have the norm of the solution. And this curve, the red curve, is how these 2 errors evolve as we change alpha. And here we are increasing the value of alpha. So when we go up here, alpha is very small. When we go down there, alpha is very large. So this situation, for this solution, we talk about under-regularization. So we didn't throw away enough information and we get rubbish. If we go here, we throw away almost everything, so we see nothing. And the key is to be somewhere here where we find the real solution. And this kind of representation is called L-curve. You will see it. But all this I'm telling you is common to all near-field methods. So the solution procedure and the problems one faces is the same. And so now I wanted to talk very shortly about 3 methods. The third I will leave to Rick, so it leaves us 2 methods to show you the possibilities there are to solve this near-field problem. So the first one is the inverse boundary element method. And in this inverse boundary element method, well, long ago, in the beginning days of these activities with near-field measurements, people were very hopeful about boundary elements because, as you see here, you can define a very fine mesh around your source. And at a certain point in time, say 20 years ago, people thought one would be able to use, let's exaggerate, 5 microphones and find source information at 100 mesh points. So people have somehow the illusion that they could have a very high resolution at the source by using these boundary elements with relatively low number of microphones. Well, that's impossible. That's impossible, and it's impossible because there is a fact of life which says that the things you cannot measure, you cannot know. So if you measure 5 points, you will get information for 5 points. And if you measure 100 points, you will get information for 100 points. And that's it. So this made, in the end, boundary element-based methods not so attractive. Of course, they give you a beautiful interpolation of the source. But interpolation and resolution are 2 different things. But anyway, it's an interesting method. And it is based, well, on this integral equation, the Kirchhoff-Helmholtz integral equation. And for inverse boundary elements, normally people use the most simple implementation of this. So they use direct collocation, which means that one evaluates the integral at the nodes of the mesh. So per element, one evaluates the integral. So one takes, let's say, one assumes that the variables are constant in one element. That is what one calls the collocation, direct collocation method. So, and the way to solve it is first to solve the field on the surface, and then solve the radiated field. And if you play around a little bit with the matrices, this is my point, one finds this expression, which is the one we saw in the beginning. So simply source information, transfer matrix, pressure information. So same structure as we had, only based on a computer model of the source. The advantage of this method, as I said, is that it allows you to describe irregular surfaces, and it gives you a very good interpolation of the field at the source. The disadvantage is computational cost. It takes time to make the model, and it takes time to work out to solve the map. Okay, so then people thought, oh, this takes too much time and it doesn't really help us, so can we do something easier? And the answer to the question, can we do something easier, is the equivalent source method, which is a very nice method, which is, judging from publications, having a revival lately. Because lately, if you see work about near-field acousticography, 4 times out of 5, it will be equivalent source method. So what is the equivalent source method? Here you have 3 possibilities. So you will see it in many, many different forms, but basically it is that one places monopole sources either at the surface of the real source or on a surface around the source, or even easier, on a plane in front of the source. You will see all these things. Last week I saw another one with sources here also, so like half a box around the source. So many combinations are possible. Spheres are also possible. In any case, the point here is one chooses a number of monopoles, and one tries to describe the source with these monopoles. And then, of course, one gets very easy expressions, because the pressure somewhere in the field is the summation of the source strength of the monopole, so that's the Q times this free space Green's function. And then, if we organize it in vector matrix form, again, we get exactly the same kind of expression. So we get Q times this transfer matrix is the pressure. So the same. So we will solve it in the same way, regularization and so forth. And now it's time for Rick to talk.
Okay.
Thank you for your attention.